So you're asking about induction. So if I have whatever my objects are ABC, and then I have a natural number n, and then I have my assumptions, and then I have my goal, whatever it is. Once I have an n, I can say induction on n, induct on n. Yeah. If I don't have a natural number n, if I have here's another situation. I have objects ABC, I have assumptions, and I have a goal. And the goal is there exists an L so that for all n less than n, yada, yada, whatever. Induction doesn't work. Induct on what? I don't have a natural number. Induct on n doesn't work because n is inside of something.
The last problem. Now there's like a 6K something.
Yes.
So that kind of looks like the second.
So you're talking about problem set 8, the last problem? Very good. Oh,
I think it's the
third problem. Oh. Yeah, by the way, I meant to ask if you guys wanted to do any of the problems together in class. So far, no one has asked for them. Okay. So should we go through this? You want to talk about it? So let's induct on little n. Is this big enough? You can see in the back. So induction prime on little n with n hn. Okay, so if it's 0, then use 0. And that's done with that goal. Now, how about this goal? What value of k? So, yes?
It's like when you apply the induction prime, we already had an n.
Exactly.
Okay.
Exactly. We have an object n. The reason you can apply, like I can't apply at this point, for example, I can't say induction prime on k. What k? There is no k. I mean, I say here there exists a k, but that doesn't mean I have it. That's what the choose.
Yeah.
So this is going to complain. I don't have a k. I don't know what you're talking about, k.
What if the problem is formulated instead as like you don't have the object n, but the goal says there exists a k for all n?
Then you still, if you don't have an object, you can't do induction.
So
on that.
Can it just be a poorly formulated problem?
No, the problem might still be solvable. It just can't be solvable by induction at this moment.
Okay, but in my head, like those two formulations are mathematically equivalent, right? Like if I were to say goal, there exists k such that for all n. And then like whatever the statement was.
Like n times n plus 1 times 6n plus 2n plus 1 is equal to 6k.
Yeah.
So this is not true because the order of the quantifiers is backwards. You're saying there's a single value of n, of k rather, there's a single value of k, so that no matter what n is, 6 times k is going to be this. Well, that's just not true.
So if it were the other way around.
Yep, let's exactly. In fact, there is actually no difference right here for the original goal. There is no difference mathematically between what we're being asked to prove here and what we're being asked to prove here. The fact that you're introing n is just that what this wants is a function from n to a proof that there exists a k, yada yada. And by saying intro n, you're just saying, okay, just give me the argument of the function, and I have to construct the function. As opposed to this, which is asking for the function, not having given you the argument. Those are identical questions mathematically. Does that make sense? Yeah. So you don't need me to go on?
Yeah.
Okay. What value of k do you use? You do a little algebra.
Yeah. Something.
First, you have to get this k out. So choose k, hk using hn. Okay, and now we have that value of k. By the way, at this point, you could do induction on little k if you wanted to. Now you have a little k. You could do a double induction. You can do an induction and then another induction. If you have a natural number, it doesn't mean it will work. Doesn't mean you can prove the theorem that way. But if you have a single natural number in your list of objects, you can induct on that number. Because to prove a theorem about this number is to prove a theorem about something whose definition, whose very definition is 0 and successor. So what this really says is, for all things that come out of a 0 and successor process, this happens, which is literally what induction says in another way, using other words.
Yeah.
Okay, thank you.
Question that I have. But if you have like for all and
Let me write. Yep.
like how do you decide whether to use that from capital or intro?
Right. So we had a goal. We had a goal that was for all little n less than capital N. Yada yada. How do you decide? Well, how do you prove a theorem? There is no. If there was a mechanical process that proved theorem statements that are true, I would be out of business. Right? So how do you learn how to decide which is which? Do a whole mess of problems. That's how you learn. Okay? Experience is what teaches you whether you're going to be able to, whether right now you want to induct or not. In that instance, I'll tell you how. Induction is a process that starts from n and moves seamlessly to the following values. So suppose you introed n at this point. Okay, so if I do intro n hn, then what I get is I have a natural number, so my objects are natural numbers n and little n, and the hypothesis that n is less than n, and now I have my goal that I want to prove. Induction on little n is not good. This will not continue, this hypothesis will not continue to hold as you move through successors. At some point, I'm going to get in trouble. And I don't want to apply induction on capital N at this point, because again, I'm going to have to face different conditions, whether, if capital N starts at 0 or if capital N is a successor. I have to wait until little n is larger enough, is small enough than the successor of n. So that's why in this case, you do not want to do this intro. You already have a capital N in one of your objects. You want to immediately jump to induction on this capital N. Because it's a statement, the little n is really, I wouldn't even think of it as a natural number. I would think of it as a number that's being indexed from 0 to n minus 1. So that's not it is a natural number, but you can think of it as something that's not a natural number. Because natural numbers should be 0 and successor. So if something's not true for 0 in all future values, then that's not a good place to induct. Yeah, okay, so there is a general principle, and that's it. Does that make sense? Did I answer your question? So I'll try to write it down. Principle. This is less about when to use induction and more about when not to use induction. If some property does not continue to hold, and there are counterexamples to this principle, so it's a very loose principle, but as a weak rule of thumb, if a property does not continue to hold for the successor of n, in other words, i.e. n plus 1, then that's not a good variable to, that is not a good variable for induction. Okay, that makes sense. All right, let's jump back into our theorem in progress. Our theorem in progress is now, we're almost done with the algebraic limit theorem. What question? No. Our theorem in progress, which is called product limit in the case when both are non-zero, and of course your homework will be to remove the non-zeroness, is the following. So theorem, we talked about this last time. I think we can quickly remind ourselves of the proof. You have an going to L, and L's not 0. You have bn going to m, and we also said that m is not 0. We have cn is equal to an times bn, and the goal is to show that cn goes to L times m. Okay, this is called HA. This is called HL. This is called HB. This is called HM. HM is the non-zeroness. This is called HC, the hypothesis on C, and then this is our goal. Okay. Sketch of a proof, although it'll be pretty close to a formal proof. Let epsilon be given and assume that it's positive. This fact we'll call H epsilon. And so we eventually will want, at some point, I'm going to skip some lines, we're going to want to look at Cn minus L times M, which of course is An times Bn minus L times M. And the big idea last time was, Joe? Exactly. Add and subtract. Only change one of them at a time. We change both A to L and B to M, and that's too much. So we're only going to change one of them at a time. I don't know, Bn times L plus Bn times L, and then minus L times M. Okay. And in fact, a better way to group that is, let's write this as Bn times An minus L plus L times Bn minus M. Okay, does that make sense? All right, so that's just ring. And then we're going to say we're going to break this by I'm simultaneously doing the triangle inequality and the fact that products, what is that called? Abs-mol or something. Okay, so this is abs add. At some point, we'll want abs-mol. All right, Bn, now Bn is going to be bounded uniformly because it converges. Yeah, we have a theorem. So we have bounded of converges, and maybe there's a non-zero version. And for your homework, you're going to prove the not, or you already are proving the not non-zero version. Bounded of convergence, B, M, and the fact that B goes to M, and the fact that M is not zero. So that's going to tell us something like, so we'll choose a K. We'll choose a K and maybe HK or something using this. And that means that this is bounded by K. L is L. We'll make the An minus L less than, we did this last time. Yeah, epsilon over 2K. We'll make this one epsilon over 2. We'll make that one epsilon over 2. They'll add up to less than epsilon. Okay. This will be less than epsilon over 2 absolute value of L. Of course, at some point, we're going to need that absolute value of L is positive. We'll need the positivity of K. The positivity of K, somebody was asking me, do I actually need to include the positivity of K in our proof of boundedness? And you'll see right away why it's convenient to already have that and not have to fight with it more. So we'll also have it something that gives us the positivity of K out of this. Okay, and then we're done. Should we jump right into the proof, but without doing a full formal proof? Let's do it. I will keep this here as usual and slide this over as usual, just so we can look at it to see what we might want to do. All right, step 1. Intro. Yeah, give me epsilon. Let epsilon be given. Intro epsilon, H epsilon. All right, we've got our epsilon, we've got our H epsilon, we're going to need a capital N. So we're going to need a capital N. This we could have done with our eventually, by the way. But we proved an even better theorem, not just eventual boundedness, but just completely uniform boundedness. We're going to need N to be large enough so that this happens, and we're going to need N to be large enough so that this happens. So let's get both of those. I guess I have to record the positivity of epsilon over 2K. I don't have 2K yet. I need to get the K first. So the K comes from the theorem called bounded of convergence but I don't remember what that theorem is called, so I have to look it up. Bound of converge non-zero. Okay, that's our theorem. So let's choose KHK using this. Now, what does this theorem need? It needs a capital, the sequence A. It needs the real number L. It needs HA. It needs the non-zeroness of L, and then it'll give us what we want. Let's see. Can I slide this back over? Oh, that's annoying. Ah, wait, I can't scroll up anymore? Do an apply that does nothing. Got it? Great. Now I can scroll up. Okay. You notice what it gave us for HK. When I said choose KHK using this theorem, it gave us a K, a real number K, and then it gave us HK, which is two facts. So we can use HK.1 and HK.2 to get these facts out. Or we can go back and change our choose and break HK into a couple more things. So let me retry this step. And instead of saying HK, I'll do K pos HK. So it's choose K, K pos, and HK. And that will give us, that'll just break this up for us. So now we have the fact that K is positive and this extra condition on the boundedness of the sequence A. By the way, I applied it to A. In our sketch, we applied it to B. Should I keep it like our sketch? We wanted the uniform boundedness of B, not A. So let's retry this one more time. We'll stick in B and M, the fact that B converges, and the fact that M is non-zero. Okay, so now we know that Bn is bounded by K. Great. All right, we're going to use epsilon over 2K. So let's have F1, which is that epsilon over 2 times K is positive by bound. Great. We're going to need the positivity of this. Question? No. Roger, anything? Please, if you have questions, ask. I'm glad you can get an answer from your classmate, but it really will help lots of other people if you also ask me. We need the positivity of epsilon over 2L. Experience shows we need the positivity of L. So let's record that as well. Have L pos, which is not L itself, but its absolute value. That's by apply abs pos of non-zero, and the non-zeroness of L is HL. So far, so good. Everybody with me? I'm not going too fast. Then let's record the fact that epsilon over 2 times absolute value of L is also positive, and bound will take care of that for us. Very good. And now we're ready to make n so large that both of these things happen. So we can specialize HA to this value of epsilon, and using this proof, that'll give us an existence of a capital N, or we can jump straight to choosing that capital N. So let's be a little slick. Choose N1, HN1, using HA with epsilon replaced by epsilon over 2 times, let's see, yeah, 2 times K, and the fact that that is positive is F1. Do you see why this is going to work? HA is a function. It takes the value of epsilon, takes this value of epsilon. It takes a proof that that value is positive. That's what F1 is. And it says there exists an N, so that yada yada. So we can jump straight to, okay, give me that N. So our proofs are going to start getting shorter and shorter as we get better at this. Okay, so we have our N1, we have our natural number N1, and the fact that for all N greater than N1, we got this bound. Beautiful. Now let's get our other bound. Can I just copy and paste? I think so. Choose N2, HN2 using epsilon over 2L and F2. There's our other HN2. Brandon? Lean won't let you get away with it. I'm glad you guys won't either. Yeah, of course, we would have gotten very stuck very shortly, and we would add the backtrack. So now we have that this is bounded by epsilon over 2L. Great, now we know what capital N to use. 2. Now give me my N and HN. Let's record have HN1 is that N1 is less than or equal to N by bound. Have HN2, which is that N2 is less than or equal to N by bound. Okay. And now we can specialize HN1 and HN2. So specialize HN1 to N together with HN1, and same thing with HN2. All right. So now we have our bounds. We are sitting on this pair of inequalities together with the inequality. Let's get the inequality that not just for all n, but for this value of n. So let's specialize HK to n. So now I think we have everything. We have the positivity of L. That's right there. We have that Bn is bounded by K. We have that An minus L is bounded by this. We have that that's bounded by that. Beautiful. We just have to turn Cn minus L times M into An times Bn. Here's another trick. You don't have to specialize HC. You can just rewrite HC. So what it's going to do, what the rewrite is going to do, is it's going to go to HC and it says for all n, Cn. Now, I don't know what value of n yet to use. This is true for any value of n. But if I see C of something, I can replace it by A times B of that thing. I'm going to look at the goal. I'm going to find a C. I'll know which value of n to plug in. So you can skip the specialized step. That was just for us to, that was a pedagogical device. Okay, Lean is smart enough to see through those things. It doesn't need the pedagogy. It knows how to prove theorems. I'm trying to teach you guys how to prove theorems. Okay, that makes sense? So now we have this. Great, let's start chaining things. What's our next, should we make this? Oh, no, it's not a good quiz. What's the next line? Jeffrey.
Equals like the thing plus
Perfect. This thing is equal to something else by ring an F. What is that something else? So how did we do it here? We took the Bn out and made it An minus L, and then we took the L out and made it Bn minus M. Does that look right? Bn times A minus L, yes. L times B minus M, yes. I'm going to make a little note that they should make these windows get larger so that you can see the whole thing. It's larger here, that's good, but it's not large enough here that when you keep writing it. Make, what is that? The execute window grow on long inputs. Okay. Hopefully we'll be able to help with that. All right. So we've got our first line. What's our next line? Triangle inequality. Come on. You could rewrite. We don't need to rewrite because we're going to just chain a bunch of inequalities that add up to epsilon. So have fact 4 is that this is less than or equal to the same thing, except I'm going to break this and that. And that's by apply abs add. Okay. So this is equal to this, which is less than or equal to that and that. How about this part? Let's isolate this. Have F5, which is that this is, what am I going to do with this?
Well, right. I guess like what B and F times that by F.
Exactly. Let's keep working with this for a minute. Whoops. Come on. I want to grab. Sometimes the hovering is very good. And then there's other times. Okay, so F6 let's say this is less than or equal to, I wonder if it can do it both at once. Do you think it can? Or do you think bound is going to give us trouble? Should we try? This is bounded by K. This is bounded by epsilon over 2 times K. Let's see if it'll work. I really wouldn't rather not be embarrassed, but Lord knows it wouldn't be the first time. By bound. It did it. Did it really do it? I guess we'll find out. It says it did it. Because it's not smart. Because it's sometimes it.
What would you do if it didn't work?
I would do them one at a time. I would say Bn times An minus L is bounded by K times An minus L. And then K times An minus L is less than K times epsilon over 2. This is a work in progress. Yeah. So it seems we haven't, it's a have statement. So I don't really know if it worked or not, but we'll find out. Finally, we should know that this thing is equal to, let's have F7, which is that this is just epsilon over 2. Let's cancel the K on top and bottom and just get an epsilon over 2. Will bound please do that? Or actually, bound is not going to do it. Bound is not going to do it. What will? Field sim. Field sim knows that K is positive somewhere. Yeah, we know that K is positive, so field sim should do this. And it does. At least it looks like it does. Beautiful. So let's follow the chain. We're here. F3 gets us some algebra. F4 gets us triangle inequality. F5 breaks those up. F6 applies the bounds individually, multiplies them together. F7 combines them to say that this bit of it is bounded by epsilon over 2. Now we do it again. Have F8, which is that this part, come on, this part. It's faster just to write it out, isn't it? Have F8, absolute value of L times Bn minus M is equal to those two absolute values by apply abs mul. Let's hope this continues to work as nicely as it did. Have F9, which is that this is less than or equal to, now L is just L, there's nothing to do, but Bn minus M is bounded by epsilon over 2 times absolute value of L. Bound should do this. And it does. Come on. Okay. Maybe we're getting a really long context window. It's something that get fun. All right, great. And now these things add up to epsilon over 2. And have F10 that this is equal to just epsilon over 2 by, again, field sim should just do it. We know that L is positive, but there's nothing to do. Okay, beautiful. Now Literith will chain F3 with F4, with F5, with F6, with F7, with F8, with F9, and with F10. F3 to F10. Literith, F3, F4, F5, 6, 7, F8, F9, and F10. Huh. What am I missing? What am I missing? F3, did I mistype something?
HM2, H capital N2.
H, yeah?
I think one of your arguments was left over from HN1.
When I did HN2?
Yeah. I think it should have given you, I mean, there was a error, but it didn't pop up.
Oh. Let's find out.
Or maybe H little n2.
Do I just have to wait and it'll load? There we go. Just have to refresh.
Oh, this is.
It looks like the first error is the linearith. It looks like it took everything else. So what's wrong with the linearith? Let's see. an minus bm times L plus n. That's that. That's equal to this. This is equal to this, which is less than or equal to that. This bit is equal to that, and that bit is less than that, and that bit is equal to epsilon over 2.
Oh.
What did I do?
Like, so for F6 and F9.
Yeah.
Less than or equal to, but we're trying to.
Oh, thank you. Thank you. Thank you. Thank you. Fantastic. It's right. It is right, and I'm wrong. And here's where it's right. So let's go back to our little sketch here. Well, this is less than or equal to, but these are strictly less than. So it's absolutely right. The computer doesn't lie. It sometimes makes you want to throw something, but it definitely doesn't lie. This is strict. F6 should be a strict inequality, and it is enough to do one of them as a strict inequality. What's the last one? F9. I'll redo F9 as a strict inequality. Maybe I can just do it right here. F9 is a strict inequality, and that should still go through by bound, and now linearith goes through too. Okay. Okay, so thank you. The problem was I was being sloppy with my inequalities being strict or not strict. The things that we came up with proved less than or equal to, but the goal was a strict less than. Okay, any questions? Should we write this out in natural language? No, everybody's happy with that. Akil and then Sabi. Why does it accept F6? Because Bn is less than or equal to K, but An minus L is strictly less than. What do you mean, why does it accept F6?
What does it accept it be less than the B? Oh, wait.
This is less than or equal to epsilon over 2, but this one is strictly less than epsilon over 2. And it knows how to put those two together. I need a strict inequality somewhere, and then the possibility of equality is broken. Okay, any questions? Stop it.
Like, I guess like step by step, I can understand the tactics you use and stuff, but can you help me gain like some like mathematical intuition?
Yes. The mathematical intuition should be right here. The key, everything was systematic except for this. Let me highlight it. This is the only step where we used our brain. This is mechanical. You have two things added together. We're going to hit it with the triangle equality. That's mechanical. What's not mechanical? Well, and here you have to do, okay, so there's two places where you have to use your brain. Here you don't really have to use your brain. It's like, I'm going to make this epsilon over 2. I'm going to make that epsilon over 2. This is bounded by K, so I need to make the product bounded by epsilon over 2, so I'll make this as small as epsilon over 2K. This is bounded by L, so I have to make that. The only idea is to change things one at a time. And you're just going to get a lot of exercises that change things one at a time, and you'll get used to it. John.
Is there like a geometric interpretation of
Yes.
that big thing?
Excellent question. Excellent question. That is exactly what you do, by the way. You guys know the product rule? I mean, we just rediscovered the product rule. You have F and G, and how does the product of F and G change? You change F first, leaving G alone, and then you change G, leaving F alone. That's what we just discovered. It's the same principle right here. This is the change in the product of F times G. That's what a derivative is. This is the change in F leaving G alone, the change in F leaving G alone, and this is leaving F alone and changing G. Okay, and purely geometrically, if you have F, this is F changing and this is G changing, and you're taking their product, products are rectangles, that's what products are. Maybe it's better to think of like, this is the value of F and this is the value of G, and now you're going to replace F by F plus delta F. and you're going to replace G by G plus delta G. And what you get when you do that, so the difference between the big rectangle and the little rectangle, F times G. So if I take that away, the sum of these three things, that's what this is measuring. And it's delta F by G. This is F prime times G. This is delta G by F. This is G prime times F. And then this thing is too small. This is delta G by delta F, which is, you know, microscopic on the scale. Really what you should think of is here's F and here's delta F, and here's G and here's delta G. And the rectangle is really like this. And this part is just too small to notice. This is the product rule, geometrically.
It's been years since I saw the product on the side.
I don't know if anyone's ever explained the product to you geometrically, but this is what's going on. It's just rectangles. Joe. Oh, yeah? Good. Grant's, yeah, one of my favorites.
Why is this the same thing as?
Yeah, because we want to change the product of two things. We want to change A to its limit and B to its limit simultaneously. We're taking the product. And the way to do it is first change F. First, you send A to L, leaving B alone. So that's what this is. Send A to L, leaving B alone, and then send B to M once A is already equal to L.
Kind of the math trick is like, we can do that, insert the 0. And since we're trying to prove a bound, you can like separate them. Like if we're in like a different territory where we want equality or something, this trick is not as useful.
Analysis is all about less than signs. In fact, if I were even sloppier than I already am, I would just put less than signs everywhere, not keeping track of where it is or isn't an equals. Let me take them off because, but in my papers, I don't even write equal signs. I don't know what an equal sign is. It's just less than or equal to. Everything's less than or equal to, even if it's an equality. I don't care.
Is it almost better to think in that kind of sloppy way, or is it?
It's very flexible. If you think in a sloppy way, then you can see big pictures. I find you see big pictures more easily.
So there is an advantage from problem solving perspective.
I think so. Like I just need to make progress. Where am I going to get that progress from?
I mean, you use whatever information you need, like how much strict of information needs to be in order to get the right bound.
Yeah. Okay, more questions? Everybody make sense? If you had problems like this on the test, you'd be able to do them, to solve them with practice. So let's just review. Let's recall, since maybe it was quite some time ago, we know that if AN goes to L and C is a constant, C times AN goes to C times L, right? We proved that at some point. So that was one thing that we proved. Another thing that we proved was that if AN plus BN, if AN goes to L, I'll just make an assumption out here. AN goes to L and BN goes to L. Then our goals, this was one goal that we proved. We had another goal, which was AN plus BN goes to L plus M. We proved that. That was like one of the first things we proved when we started this sequential limit interaction. Thank you very much. You see how easy it is to make a mistake. We previously proved that if you had AN going to L and L wasn't 0, then, so goal, if that's our assumption, then goal was 1 over AN goes to 1 over L. We proved that. And just now we proved that AN times BN goes to L times M. So if you chain these 4 things together, that's the last thing we proved. You chain these 4 things together, what it tells you is any rational function, you can get summation, you can get scalar multiplication, you can get multiplication, that means you get polynomials, and you can get inversion. So if you know that, so corollary, if AN goes to L and BN goes to M, what's that? Did I misspell? some people say corollary, and some people say corollary. Yeah. Then what happens to an squared plus 2an plus bn over b3bn plus 2 minus an squared? What does that go to? Yeah, it's L squared plus 2L plus M over 3M plus 2 minus L squared, assuming this denominator is not 0. Okay, and it's just a mechanical combination of these processes, and you can get any rational function. So any rational function commutes with limits. You can take a limit and then apply the rational function, or you can take the rational function and then take the limit, and you'll get the same thing. Okay. All right. Very good. Let's move on to, we're inching closer and closer to the point where we actually need to know something about the real numbers. What are they? Very good. Let's do the order limit theorem. This is a very nice and simple theorem. So the algebraic limit theorem was about exact operations. Here is a theorem that is not about exact operations. Let's do it in our usual way. So this is the order limit theorem. Order limit theorem. It's a very obvious theorem from a human standpoint, and then the question is, how do you actually prove it? The theorem says you have a sequence an that goes to L, and you have this hypothesis called HK, which is that for all n, an is less than or equal to k. So the picture is, here's your ans, and they're getting closer and closer to L. And you know that there's some value of k. I'll put it, I don't know, over here. And all of the ans are upper bounded by k, all of them. Then this picture is impossible. L can't be bigger. The goal is to show that L is less than or equal to k. Not this. I think this is a good quiz. Akil.
Like what HK says there's A of n is bounded.
So in order to say A of n, I need to have a little n. So this says for all little n, A of n is bounded by k. If I say A is less than or equal to k, I don't think Lean will accept it because, so the reason I can't say A is less than k, compare A is less than k. A is a function. A, the type of A is n to r. K by itself is not a function.
No, my question was,
Oh.
why can't it be just like, I don't know what it's called, it's like C, D, D, D.
Oh, the sequence is bounded. Yes, we know that the sequence is bounded by something. Sequence bounded doesn't tell you what the bound is. Right? Maybe I'm not understanding your question. So, instead of saying this, we could just say an is bounded, seek bounded an. Is that what you're proposing? Okay, the problem with seek bounded an is it doesn't tell you what the value of k is. So we need a better thing than sequence is bounded. We need a sequence is bounded by. We can add that to our definition, sequence is bounded by, so you can specify what the k is, and then this will just say sequence is bounded by a k. Yeah, we can certainly add that. I could probably even add that while you take your quiz. Let's do this. I think you can do it. I think you can do it. You need one idea. It's too much. Is an idea too many? Should I give you a hint on how to get started? Do it in natural language. I think at this point, we're getting good enough at our translation from natural to formal. That just do it in natural language. See if you can prove this theorem. You have a sequence A going to L. You know that for all n, A is bounded by K. Your goal is to show that L can't be bigger than K. L is less than or equal to K. My wording just now was a hint. While you do that, I'm going to see if I can execute. Whose idea was that? Brandon? Yeah. I'm going to try to execute your idea. So let's see. This is order. I'm going to add a definition. Um, okay, so there's now a new thing called seek bounded by. Seek bounded by it says, unlike seek bounded, sequence bounded was the absolute value of the sequence was bounded. Seek bounded by says that the sequence is bounded above by some number m. And you have to specify what that number m is. And now, let me just reload this. Now it says the sequence A is bounded by K. Anybody stuck and need a hint?
Can you say what you said before again? Just, I guess.
What I said about when I said I gave you a hint?
Yeah.
When I said I gave you a hint, the hint was that this can't happen. So the goal is to show that it can't be the case that K is strictly less than L. That's the hint. So what do you think? What did you guys do for your first step in your proof? By contradiction. So what goes wrong?
I got that combined some value of little n, for which k of n is real.
Okay. Yep. How'd you do it? Or
I
do people still want time to think? Or we more or less got it? They're still working. Give me.
Yeah, I was reading K, you can like bound it by something that's like, you know, minus K to exactly. And so like if you're proving that whatever value you are in is greater than K. To this. Yep.
Are we ready to do it? Let's do it together. Let's do it together. I don't want to spend too much time on this. Let's do it together. So step one in the proof. Yeah. Let's prove it by contradiction. Assume, what should we call this? HL or something? Or just H? H is by contra H. By contra H, contradiction, you don't have to specify what the hypothesis is. It knows we're gonna make a new hypothesis called it's not true that L is less than or equal to K. Okay, so let's have H prime, which is that if it's not true that L is less than or equal to K, then K is strictly less than L. In fact, not only is K strictly less than L, but L minus K is strictly positive. And maybe by bound will do that. Then what? L minus K is strictly positive. Some of you did L minus K over 2, which is fine, but actually it's enough to just use L minus K because we're going to get a strict inequality. Every value eventually will be within L minus K of L, which in particular means it's going to be greater than K. Jeffrey.
Specialized to more than.
Yeah, it's called HA or something. Yeah, so we can specialize. In fact, we can jump straight to choose NHN using HA with epsilon replaced by L minus K, and we know that L minus K is already positive. Does that make sense? So now, what's our goal state? We have natural number n. We have the hypothesis Hn that for all n greater than capital N, absolute value of an minus L is less than epsilon. Epsilon is L minus K. That's what we just added to the goal state. Does that make sense? And what value of n should we specialize Hn to? How about capital N itself? And then why is n greater than or equal to n? Bound will do that. So we can jump straight to by bound. Okay, and that will make Hn say a capital N minus L is less than L minus K in absolute value. Beautiful. You guys remember the theorem abs LT? That an absolute value is less than something if and only if. So this will change Hn to L minus K, I guess negative L minus K is at least An minus L, and An minus L is at most L minus K. And so what? We're almost there, other than Jeffrey. Is everyone following along, or am I going too fast? I'm going a little too fast. Suhas, did I lose you? No. Arjo? Okay. Sam?
Trying to go a different.
Oh, how did you do it?
About triangle inequality, adding K and subtracting K inside the AN minus L.
Okay, yeah, you can do that too. This is just a slightly faster treatment. The point is negative L minus K, that's this lower bound for AN minus L, which means if I add L to both sides, this is negative L plus K, I'm gonna get A at this value of capital N is strictly greater than capital K. And that's gonna contradict the other thing. Okay, so we're almost there. We just need this condition. This condition, by the way, is now called, as of a second ago, this is called seek bounded by A K. So go ahead, Jeffrey.
First, like, specialize.
Exactly. Specialize HK to what value of capital N? I mean, I give it away to, with little n equal to capital N. And now we're done. If you, it's linear arithmetic in using HK together with HN.1. It'll be able to do it. Let's do it together. Go. Okay, step one by contra. So it's a proof by contradiction. Okay, so now we have this. So let's have H prime that 0 is less than, strictly less than L minus K. And bound should be able to do that for us. Great. That's our epsilon. So the key idea is to use L minus K as the epsilon. You could use L minus K over 2 or something. But as long as you're using something less than L minus K, and L minus K is enough, because that's enough of a window to force a contradiction. All right, so let's choose NHN using HA, where we stick in L minus K for epsilon, and the positivity of L minus K is what we just proved. So now we know that for all n greater than capital N, we have this bound. So let's specialize HN with little n equal to capital N, and why is that? By bound. And now we know that AN minus L is strictly less than L minus K. So now let's use this abs LT theorem. Rewrite abs LT, not at the goal, but at HN. So I should have said here, at HN, not at the goal. So now we have these two inequalities, and just stare at our inequalities. We have AN, if I add L to both sides, I have A capital N is strictly greater than K. And that's going to contradict this seek bounded by. For pedagogical reasons, let me change seek bounded by to say for all n, AN is less than or equal to K at HK, just so we can see what seek bounded by means. That was just for us. And now let's do linearith on HN.1. HN.1 is going to give us that AN is at least K, and HK, but not for any value of K, for the value of K, not for any value of little n, but for the value of little n equal to capital N. We didn't have to specialize. And that's the theorem. Okay. So if your sequence converges to L, but is always bounded above by K, well, then K is also an upper bound for L. We just added it. You told me to, or Brandon told me to. We just added a new thing called seek bounded by. And the definition of seek bounded by is for all n, AN is less than M. Oh, somebody told me to do that. It wasn't you? Akil, did you tell me to do it? Somebody. Yeah. Yeah, so it was you. Sorry, Brandon, I picked on you. It's Akil. Yeah, you're the reason this guy added. All right. Had you PR'd it, it would have been an extra point. There's plenty more things you guys can PR. All right, let's do one more level. Any questions on this level? Okay, so limits pass through algebraic operations limits also pass through inequalities. And for homework, you'll prove the opposite inequality. Yeah, you can hand the quizzes over to Joe, please. Let's do one more level, because now we're really starting to get to some juicy stuff. Let's talk about subsequences. We have a new thing called subseqs, a new definition. Check this out. We have a sequence A. We have a number L with an going to L. We have a function sigma from the naturals to the naturals with the property that it is a subsequence. And what does it mean to be a subsequence? A function on the naturals is called a subsequence if it's strictly increasing. You had a homework problem about a strictly increasing function. So if it's strictly increasing, if for all I and j, if I is less than j, then sigma I is less than sigma j. Okay, so that's what it means to be a subsequence. And now our goal is to prove that if you take not the original sequence, but the sequence A composed with sigma, it still has the same limit. All right, so let's think about this. Let me write it down and let's think about it. Let me slide this all the way over. Let's write it down and think about it. So here's our claim. So we learned that limits pass through algebra, limits pass through inequalities. Let's think about subsequences. So definition, sigma, a function on the natural numbers, is it's really a sequence, but I'm thinking of it as a subsequence. I'm going to call this subsequence, which clashes a bit with usually what people say, like A sub N sub K or something for a subsequence. You've seen subsequences before. No, you haven't seen subsequences. Okay, good. So if I have the sequence A0, A1, A2, and so on, that's my sequence. And then if I only take A0 and A3 and A6 and A9 and so on, that's a new sequence. It's a new sequence of numbers, which I'm just not taking all of the original indices. I'm taking some subset of the indices. So what this subsequence is trying to do is it's saying, what's the first index? The first index is 0. What's the next index? The next index is 3. What's the next index? The next index is 6. And what's the next index? The next index is 9, and so on. Okay? So that's a subsequence of the original sequence. And what's going on mathematically is you're just speeding up. If this was AN, whatever AN is doing, if this is AN, then our subsequence, which is A composed with sigma, what's the value of this at N? It's just A at sigma N. That's what composition is. It's just re-indexing, but not reordering. We're not saying you take this value and then you take this value, but then you go back to that value or something. It's just skipping a few steps in the sequence. So maybe we'll take this value and this value and this value and this value and that value and that value. But to actually plot them where they go, I have to compress everything. So maybe the compression will be in green. So here's the first value, and here's the second value, and here's the third value, and over there is the fourth value, and over there is the fifth value, and so on. Okay, so all that's happening to this sequence is we're just compressing it, just removing some of the entries and sliding everybody down. That's composition. So usually people write it like this. You can't see that color, right? Let's go back to blue. Usually people write subsequences like this. I will call the subsequence function, the subsequencing function, a subsequence. So is a subsequence if it's strictly increasing. So I less than j implies sigma I is strictly less than sigma j. Okay, so it's a strictly most people would call this not a subsequence, but they would call it monotonic increasing. Monotonic means either you're increasing or decreasing, and then strictly is that this is not less than or equal to sign here. It's not a less than or equal to sign, and increasing. Okay, so I don't want to just sit on the same value. I'm not allowed to have an equal sign here. That would allow me to pause at some value. I'm not allowed to pause. I'm just removing some values and scrunching everything. Does that make sense? So that's what it means to be a subsequence. At least what I'm calling a subsequence is this sigma function. And of course, what I really want to think about is the composition of sigma with A. And the claim is, here's the subsequence theorem, subsequence limit theorem, if you like, is if AN goes to L and sigma is a subsequence, then my goal is to show that A of sigma n also goes to L, goes to the same limit. So I can't, when I do this squishing operation, if AN went to L, got closer and closer to L, no matter which choice of points I take from the original sequence and squish, I still get a sequence that's getting closer and closer to L. Stop it.
This assumes that all subsequences have to be true.
All subsequences get arbitrarily large. Yes, and I mean, any sequence is infinite because it's a map on the natural numbers. And then there's infinitely many natural numbers. So it's an infinite list, but in fact, that infinite list is going off to infinity. Because it's strictly increasing. Akil.
Can you say that like the n for the composition will be less than?
You had a homework problem. If you recall, you had a homework. So let me remind you, recall. And in fact, that'll be essential to what we're about to prove. Where's our homework problem? Problem set 8, exercise 1. Nope, that's not the one. It was problem set sequence. Okay, I have to go a little bit more slowly over. Problem 4 of problem set 8. Here it is, subsequence greater than or equal to. What you proved in problem set 4, in problem set 8, problem 4, is that I didn't call it a subsequence yet, but you see it says if sigma is a subsequence, then it grows at least linearly. It can't grow slower than the function, whatever this sigma is. So recall, this is problem set 8, number 4. If sigma is a subsequence, then sigma of n is at least n. So whatever the graph of sigma is, I mean, it might start at 0, and then it better go to 1, and then it better go to 2. It might jump to 8. It might jump to 27. It might jump to 28. Whatever it is, it has to start jumping. It can't get below the line y equals x. Okay, so this is a crucial fact, and that crucial fact I now gave a name, and that name is subseq greater than or equal to. Any subsequence grows at least linearly. Okay. So how should we prove this? This is actually very, very easy to prove, even though it seems like an extremely powerful theorem. The proof is completely elementary. There. Exactly right. Okay. So let's intro epsilon and h epsilon. So now our goal becomes there exists an n, so that for all n, at least n, a composed with sigma of n is less than minus L is less than epsilon. And I mean, the way you would write this in natural language is a sub sigma n. All right, that's our goal. Given this epsilon, let's choose n hn using ha with this epsilon and the fact that epsilon is positive. And then just use this n. I'm sorry. No, not use this n. Use what? Sigma of n. Use sigma of n. And now intro n hn. So yeah, let's do it here. I think this is one of those that it's easier to follow along. This is where having the theorem prover really helps. Okay, let's remember what's going on. We have seq lim a sigma. So if I intro epsilon h epsilon, my goal has become to show that there exists some n. Now I know seq lim is that given an epsilon, there exists some capital N. So let's just specialize. Let me go a little bit slower. Specialize HA to this value of epsilon and H epsilon. Okay. I know that for any n greater than capital N, AN minus L is less than epsilon. I claim that we can use that same capital N. Let's choose this capital N. So choose capital N, H capital N using HA. Now we have this capital N, and let's use this capital N. Okay, let's intro NHN. So I have to show that A of sigma of N is, in fact, maybe it'll be easier to see it that way. Let's change what we're trying to prove to A of sigma N minus L is less than epsilon. Again, this is purely pedagogically, just so we have something slightly nicer to look at. Okay. We know that N is at least capital N. I don't want to specialize Hn to little n. I want to specialize it to sigma of N. In order to do that, I need to know that sigma of N is at least capital N. But we have a theorem. Let's call this fact 1, which is that N is less than or equal to sigma of N. And that's by applying the theorem called subsequence greater than or equal to. Subseq greater than or equal to, I need to be given the fact that sigma is indeed a subsequence. That's H sigma. H sigma is this fact that we want. Aha. So capital N is the lower bound for little n, which is the lower bound for sigma of N. So we have F2, which is capital N is less than or equal to sigma of N. And that's by bound, although linearith, yeah, let's do it kind of properly. Linearith of Hn and F1. Okay, now I can specialize H capital N to what value of little n? Sigma of N. Together with the fact F2, that is indeed lower bounded by capital N. And that's exactly what we wanted. Apply Hn. Cool. So if you have a sequence, then any subsequence of that sequence converges. That's all I have to do. I just have to reload. Any subsequence converges. Let's do one more thing. We only have 3 minutes. I think we can do it, though. I think we can. There we go. All right, let's do one more thing because I want to show you maybe it was Akil. Somebody was asking me last time about how do you make a new function out of nowhere. And the way to make a new function out of nowhere is the tactic let. Let is just like have. You give it a name, you say what kind of thing it is, and then you produce it. And if you want to make a function, the way to make a function is to write the word fun. Fun is it's fun to make functions. You give the dummy variable name, and then you use this maps to, \maps to symbol, and then you say what you want to do to x. So there's a map that sends x to x squared. That's how you can out of nowhere create the function that takes x to x squared, the function y equals x squared. Okay, let's look at our problem. We have a sequence an. Our assumption is that an is plus or minus 1. We've seen this sequence before. It does not converge. There exists a sigma and an L so that sigma is a subsequence, and when you compose A with sigma, that does converge, and it converges to L. Can you think of a subsequence of these values for which it does converge? John?
Yeah, so I think you can let L just be 1.
Okay.
Sigma would be just the map.
So L is a real number, and here I can just say colon equals 1. There's nothing to prove. Let L be 1. Very good. You see, and now I have a new real number L. What I don't like, and I asked them to change this, is it doesn't tell you what the definition is. And then what should sigma be? Let sigma be a function from the naturals to the naturals. It's a function that takes n and maps to what? To what? 2 times n. Beautiful. 2 times n. Exactly right. Just speed it up by a factor of 2. Drop every odd value. Only keep the even values. Okay, so I've created out of nowhere this value of L and this function sigma. Of course, I haven't created them out of nowhere. And the goal is that they exist. So what should I do? Use sigma, and I could, in the next line, use L or comma L. And now I have two things to prove. Sigma is a subsequence. How do I break up two things that I need to prove? Split ands. Let's split up the ands. Okay, and I only have one goal. Why is it a subsequence? Well, give me an I and a J, and the hypothesis on IJ that I is strictly less than J. You have to remember what it means to be a subsequence. It's that for any I and J, if I is less than J, then sigma I is less than sigma J. But what is sigma I? It's 2 times I. So let's change what we're seeing to 2 times I is strictly less than 2 times J. Lean knows the definition of sigma. So I have to prove that 2 times I is less than 2 times J. That's linearith from Hij. Linearith Hij. Okay, next, why is the sequence converging? So intro epsilon H epsilon. Which value of n should we use? This is now the constant sequence. Not yet, but it will be. So what value of capital N? 0 or 6 or 7, whichever one you want. 41. Okay, intro NHN. Let's change this. Okay, let's rewrite HA. Rewrite HA. Ah, very good. So it doesn't see through that. So first we have to change. Let's change the goal to A of sigma n. And in fact, sigma n, we know what sigma n is. It's 2 times n minus 1. We know what L is. L is 1 is less than epsilon. Can Lean figure that out? It can, and it did. Okay, so we just looked at all the definitions and changed it to this. Now I can rewrite by HA, I think. Thank you. And now how about norm num? I mean, technically I should say this whole thing is equal to 0 by norm num. Let's get into the practice of not having naked tactics without explaining what they're doing. Have F1, which is at 0, or this thing, is equal to 0. And let's do by norm num. Will norm num do it? It did. Okay, and rewrite F1. What? Ah, the old casting. The old casting into the reals. We don't know that this is a statement in real numbers. And now I can rewrite by F1. And now it's exactly H epsilon. Okay. Very good.